Okay, dear students, welcome to this image processing session. So today I have to discuss some concepts related to image compression. So this image compression can be implemented using discrete cosine transformation. So this discrete cosine transformation is one of the image transformation technique which is present in the image transformation module. Okay, in image transformation module, we have two types of transformation. One is the discrete Fourier transformation and as well as the discrete cosine transformation. Okay, so these two are the two major categories of image transformation we can apply. Then coming back to the transformation concept, why we need transformation? Because sometimes whatever the image which is present in the spatial coordinate system, that is what we can represent the pixels through the XY coordinate system, it is not possible to make suitable amount of the compression what we can expect of it. Okay, so because sometimes we need to compress the image more and more. Okay, it may be an image or it may be a multimedia clip or it may be a video MP4 component, whatever it is. Okay, so in this scenario we have to convert the given image into another domain. Of course, we know that transformation domain is nothing but the frequency domain. And once you convert the given image from the spatial coordinates domain into the frequency domain, so what are the pixels with the dots, picture elements which are present in the spatial coordinate system will be converted into the appropriate coefficients. These coefficients can be represented by the variables u and v. And coming back to the coefficients, we have two categories here. One is a AC coefficient and another one is a DC coefficient. So this AC coefficient we can call them as an alternating current coefficient, and DC is discrete cosine transformation coefficient. So these two are the major categories based on which we can achieve the image compression. Okay. So now with all this basis, I am going to start my presentation. And then after the presentation, we will discuss how to convert this what we can say the coefficients. The coefficients contain amplitude. Okay, because it is representation of the sinusoidal wave. Okay. Then we have the frequency. Okay, and wavelength also. Okay, because once you have an image, okay, you have an image. So this is the image if you consider, and when you convert this image through the transformation technique, that is T of R, whatever the result is a sinusoidal wave. Okay, the sinusoidal wave. So this sinusoidal wave, okay, once you get a sinusoidal wave, so this has the two parts. So that is the first one is what we can say the real part, and there is another one is called as the imaginary part. Okay, so there are two types of components which are present in the sinusoidal wave. Then coming back to the imaginary part is nothing but the sine components, and as well as if you consider the real part, it is nothing but the cosine transformation. It is DCT, that is what we can say discrete cosine transformation. And in Matlab, we have a function so called as DCT2. Okay, what is this DCT2? Discrete cosine transformation, two-dimensional. Okay, two-dimensional means if you consider any image with two components, that is x and y component, we can apply the DCT function. This is the built-in function in Matlab, through which we can identify the different coefficients, that is in particularly DC coefficients with respect to the intensity values and as well as amplitude and frequency. So all these things we can find out. So first we are going to make some presentation using the PPT, then we shall implement these concepts by using the Matlab. So this is what my today's topic. So I am going to share the PPT. Just to go through some of the concepts. Yes, can you see this presentation, dear students? ಇದು ಕಾಣಿಸ್ತಾ ಇದೆಯಲ್ಲ ನಿಮಗೆ?
Yes, sir.
Okay. So So basically, already I have explained all these things. So it's a technique of the image compression is nothing but storage, or what you can say transmission of the image by reducing the storage size. So it can be compressed by reducing the values of every pixels. So sometimes it is very difficult to reduce the pixels value. So that is why we need transformation into frequency domain. So of course there are two categories, lossless and lossy compression. Under this lossless compression, so so what is happening over here, once you recover the image, once you decompress the image, it should not look like exactly the original image what we have earlier considered, because sometimes there may be some noise or distortion can be introduced. So that is why lossless compression, and of course lossless compression, the compression ratio is considerably high when compared to the lossy compression, because in lossy compression there may be some loss of data. On the other hand, lossless compression, you are going to exactly reproduce the same image what we are already have considered. Okay? If you consider the lossy compression, of course some kind of data can be lost, and that is why the compression ratio is high, very high in case of lossy compression, but the compression ratio is a little bit lesser in case of lossless compression. So coming back to the discrete cosine transformation, implementation of discrete cosine transformation in particularly, you can use this as one of the components in order to show the entropy and the energy components, because it is always going to focus on the frequency. Frequency means it is nothing but it's some sort of energy, because of course electromagnetic radiation, if you consider, if you study the pattern of electromagnetic radiation or electromagnetic waves as through the spectrum, okay? So what it is basically, electromagnetic waves are nothing but they have some sort of energy, okay? So suppose if you consider the solar energy also, the sunlight is also some kind of energy. So it has been emitted by the stars. So similarly, these kind of energies, that is in particularly the electromagnetic waves. So if you, 1 minute. Okay, if you consider these electromagnetic waves through the spectrum, you can see the waveguide also. Okay, that is the division of the light into different wavelengths. Okay, so if you consider the same electromagnetic waves, we have this what we can say the energy component. So the energy component, sometimes we can call them as entropy. Okay, so this entropy and energy, they belongs to the physics concept. Okay, so what we have to focus here, the discrete cosine transformation is one type of a transformation through which we can access these components. That is in particularly the entropy component. So if you want to access the entropy component, you have to get the amplitude. Amplitude means the highest, the peak of the what we can say the sinusoidal wave, because the image will be converted into the electromagnetic wave. That is the sinusoidal wave. So if you consider the sinusoidal wave, there may be an amplitude. Similarly, the number of times the frequency or number of times the wave is going to oscillate, we can call them as the frequency also. Okay, so that is why we have to consider all these physics terms, that is signal, frequency, amplitude, entropy, energy, and all those things, because we are discussing all the image in terms of frequency domain. That is why. Okay. Now, to perform the discrete cosine transformation on a given image, we have to fetch the image. First, we consider an image. Okay. Then, of course, the image may be a grayscale image, or it may be a color image. And if you consider an 8-bit image, of course, there may be the gray levels. They will vary from 0 to 255, because 2 to the power of 8 is 256. Since we are beginning from 0, it goes up to 255. So next, we divide the image into blocks, into 8 cross 8 matrix, because I think you people remember in discrete cosine transformation, I have given a formula, isn't it? And also we have considered an 8 cross 8 image. In the previous example, we have considered 4 cross 4 matrix, isn't it? So we have identified the cosine values based on the formula. Will you remember the DCT formula, what we have already discussed in our previous sessions? So the same concept can be considered here. Instead of the 4 cross 4 block, we can also consider 8 cross 8 block also. Okay. So now, once you apply the discrete cosine transformation, we will see that it's more than 90% of the data will be in the lower frequency component. Lower frequency means the number of oscillations are lesser, means number of times repetition of the pixels is lesser, because if you consider a lesser repetition, you can compress on more and more. If you consider more number of redundant pixels, they are going to consume a lot of memory. So that is why identify the lower frequency means those pixels which are repeated less number of times, so that we can reduce the data, or what we can say, the storage capacity. Next, in order to, for simplicity, we can took an 8 cross 8 grid. What we can say is an image can be divided into 8 cross 8 blocks, having 255 different types of intensities. And once you apply the 2D discrete cosine transformation, so what can happen? What may be the output? Just we can predict here. Okay? So now this is a typical diagram which gives some information about the DCT, that is the discrete cosine transformation. It helps to separate the image into parts, that is bands, what we can say. So now bands and different frequencies or different wavelength components or coefficients anta kuda ನಾವು ಅದನ್ನ ಕರಿತೀವಿ. For example, AC components ಮತ್ತೆ DC components. So AC means alternate current components, DC means discrete cosine transformation coefficients. Coefficients anta ಕರಿಬಹುದು ಅಥವಾ components we can call them. Okay. So of different importance. So the DCT is similar to the discrete Fourier transformation, just like we have already made a lot of discussions on DFT. That is, it is also similar to DFT. So it transformation signal or image from the spatial domain to frequency domain. That is what already I have explained in the board also. Okay, so the same thing. This is also the diagram which gives a representation of converting an image in the spatial domain into frequency domain. So now coming back to the discrete cosine transformation mathematical representation. Okay, so of course discrete cosine transformation is a real part. On the other hand, if you consider the sinusoidal part is nothing but the imaginary part. So cosine components, they will always belongs to the real part, because when you convert a given image into the appropriate sinusoidal format, there are two major components, a real part and imaginary part. And a real part, if you consider, it is nothing but the DCT components. Okay. Next, this 1D forward DCT means one-dimensional discrete cosine transformation. And if you consider, these are the different type of intensity levels. For example, it is in general N, but in our case it is 255 because we are considering a 8-bit image. So L means luminance component. Luminance in the sense intensity levels components. So they will vary from 0 to n minus 1. If so, suppose if n is 256, it goes up to 255. Now, in order to compute these DCT coefficients, so this is the formula. This is the formula through which we can find out the value for f of u, particularly the discrete cosine transformation. And if you consider the C of u, so this C of u, it belongs to this particular formula, that is 1 over square root of 2 if u component is equals to 0. That is the if you consider this component, this is u, because this is one-dimensional. Suppose if this u is not equals to 0, if it is a non-zero value, always by default C of u, this component becomes 1. So now this is the representation of visualization of 1D DCT basis functions, because any image in frequency domain can be done or can be accumulated through the basis functions. So these are the basis images. Basis images are the fundamental images. These fundamental images mele now original image na build ಮಾಡ್ತೀವಿ. So if you consider this is a band 0, f of 0, okay, this is f of 1. So this is the original image which can be extracted to create a shades. Similarly, this for f of 2, f of 3. So the number of bands, they are keep on increasing up to 7, because this is 8-bit image. So we have to start from 0 and we have to end with 7. So this is the 8-bit image. So that is why we have 8 bands here, 0 plus 7. And extended version, that is if you extend the one-dimensional discrete cosine transformation, it will become two-dimensional. Okay, so this is only one-dimensional. You can notice, so only here what kind of bars are present? Vertical bars are present. Can you notice the horizontal bars over here? Can anybody notice the horizontal bars here? So no, because it is a one-dimensional. If you have the horizontal bar and as well as a vertical bar together, so this will become the 2D. So it becomes 2D. So that is why, in order to perform this two-dimensional DCT, so this will be the equation of two-dimensional cosine transformation. That is f of u comma b, you can notice only f of u is present here. So because it's a 1D DCT function, so this is a 2D function, that is why b component is also present here, which is equals to 2 divided by square root of n into m. So n and m are the size of the grid, what we can say. So C of u in C of t. Next we have two summation. It starts from y, that is y is equals to 0 and x is equals to 0 to m minus 1. That is the size, the number of rows and the number of columns. This is the luminance concept component, that is the intensity value. Then we have the cosine transformation functions, that is one for the x and another one for y, that is rows and columns. So now if you consider this one, so this is the 2D, this is a 2D representation, because this particular image contains both vertical bars and as well as horizontal bars. Okay, and combination of these vertical and as well as the horizontal frequency components or what basis function components, it will constitute the image. Means if you want to build any image in the frequency domain, these are the basis functions through which we can build that construct. Okay, so now this is f of 0 comma 0, and if you consider a 8 cross 8 image, so this is f of 0 comma 0 and this is f of 7 comma 7. Apart from f of 0 comma 0, all the other images will contain the basis function components. Okay, so like for example, f of 0 comma 0 is the basis, okay, the lowest frequency in both the direction, that is in DC components and as well as in the AC components. Whereas if you consider f of 0 1 to f of 7, so this is f of 0 comma 1, this is f of 0 comma 1, and this is f of 7 comma 7. Here you can notice the 2D. Okay, all the both DC and as well as AC components, they are equally distributed here. Okay, so now we shall implement these things using Matlab. Okay, so for this purpose we will consider two categories of image. One is a vertical bar and another one is a horizontal bar, and also we can consider the sidebars. And let us find out how to find out the frequency components, particularly the basis function components, using Matlab. So I'm going to share the Matlab screen. Dear students, you kindly just go through this hands-on session now. Okay, I'm going to share the Matlab screen now. Dear students, can you see the Matlab window? Dear students, can you see the Matlab window?
Yes,
okay.
sir.
So now I'm going to read an image here. A is equals to so this is the image I have read. That is VB means vertical bar. So if you consider vertical bar, only horizontal frequency components are available. Let us find out how this can be done. So now I'm going to convert this image into basically this is a color image or a grayscale image. Can anybody tell me whether this is color image or grayscale image? Yes, students, can you give me the answer for this question? This image is a color image or a grayscale image? Yes, anybody? Yes, students, can you give the answer for this? I have read an image, that is vertical bar dot jpg, and can you tell me whether it is a color image or a black and white? I mean, in the sense of grayscale image. Can anybody give me the answer for this? I'm audible, dear students.
Yes, sir.
Okay, fine. So ನೋಡಿ ಇಲ್ಲಿ ಸೈಜ್ ಅಂತ ಕೊಟ್ಟಾಗ ನಿಮಗೆ ಥರ್ಡ್ ಕಾಂಪೋನೆಂಟ್ ಏನಂತ ಬರ್ತಾ ಇದೆ 3 ಅಂತ ಬರ್ತಾ ಇದೆ. So this means it's a color image because in color image only we have 3 channels, isn't it? Isn't it? Yes or no?
Sir.
So if you convert this A into grayscale image, the function is RGB to gray. RGB to gray means color to grayscale, the same image, that is A. So the A, that is A which is stored here, this will be considered as an input, and now A becomes the grayscale image. Now see here, once again I am going to execute the size. Okay, so now we have only 2 components. There is no third component because this is number of rows, this is number of columns, and there is no 3 means this is not a color image. So this will be converted now into intensity level image, that is grayscale image. Got it? Understood?
Yes, sir.
Okay, fine. Now before applying the discrete cosine transformation, we have to convert the image into single layer. So that is what we have already done now. So let us look at this image, how it looks like. Let me show off A. So if you execute this command, so the figure means a window will be displayed and the content of the image can be, we can also see it now. It is in the busy state. So Matlab always consumes some RAM. Okay, fine. So now you can see this image contains vertical bar. You can notice only vertical bar. So since it contains vertical bar, only horizontal components are present here. So how these horizontal components are present, let us find out using DCT. So this is the original image. Now I am going to apply the DCT now. That is AD, that is discrete component variable, is equal to AD. Anything you can take, not only AD, AD1 or B, C, whatever what you want to take. I have just taken AD. So DCT2, discrete cosine transformation 2, 2-dimensional on the input image. What is the variable which contains the input image? A, the small a. Okay, so I am applying the discrete cosine transformation on the input image A, because this A is nothing but the input image what I have already taken. So once you apply the discrete cosine transformation on the input image, okay, so now I have applied this discrete cosine transformation on the input image. Let us find out how the frequency distribution will go on. Okay, so for this particular thing, I am going to use a function called as the image section, IMAGESC. That is called as the image section. So what is this image section? It is going to find out the different sections of the images, like what we can say, since horizontal sections I need, I have just used the variable h here. So image section AD means the variable where DCT2 components are already stored. Okay, so now I am going to execute this. So now let us find out how this the horizontal components looks like. So that is why we have to use a function called as impixel information or impixel region. Impixel region means ಪ್ರತಿಯೊಂದು pixels na region ಜೊತೆಗೆ ಅದರದ್ದು intensity values ಕೂಡ display ಮಾಡುತ್ತೆ, frequency components ಕೂಡ display ಮಾಡುತ್ತೆ, because h is a one component which contain horizontal coefficients. So I am going to pass the value of variable h in the image, in pixel region. So let us find out how it looks like. So now you can see the window here. So here, this particular image, see we have various intensity values or frequency components which are displayed. If you go at the top, because it is a vertical bar, you know, so vertical bar will contain horizontal components. See here, only the horizontal components you can notice here. You maximize this, you can notice clearly. Okay, so only horizontal components are present, whereas the rest of the components, they are not that much, they are not going to be repeated much times. So if you compress only this band, okay, if you compress only this band, you can easily achieve more and more compression ratio. Instead of compressing all these values, if you compress only the first row, okay, you can achieve more and more success rate. So that is the conclusion of this particular and particularly the cosine transformation. Now, similarly, just like this, I am going to take another image now, okay? So, which contains only the horizontal bars are horizontal, because what we have initially we have considered vertical bar. Now we shall go for the horizontal bar. For this purpose, I am going to take another image now. So B is equals to, I am going to read another image here. I am read of horizontal bar, that is HB dot JPG. Once again, basically, can anybody tell me this particular B, that is image, it is in which type of mode, whether it is a RGB image or intensity image? Can anybody tell me the answer for this question? At the beginning, whenever you consider an image, it will be there in the grayscale mode, or it will be there in the RGB mode. Yes, dear students. So let us find out size of, which is a function used to find out the dimension of the image, size of B. So when I am going to execute this, I am going to get this information. So let's wait. It is giving this. Okay, fine. Now you tell me whether this B, the image B, whether it's a color image or a RGB image.
Color image.
Definitely it's a color image. We can easily notice the third component here. So hence we need to convert this into the RGB, that is RGB to gray. RGB to gray of B. Now once again you execute the same size of V. So the third component is gone now, because now it has been converted into the single layer image. Now same thing once again, we are going to just, you will see this image how it looks like. So now you can see here, okay. So this is an image where we can see only horizontal bars, So no vertical bars. Okay, fine. So now I am going to apply the discrete cosine transformation once again on this. So I am going to take EAT1, a new variable, which is equal to DCT2, discrete cosine transformation 2 of the input image, that is B. Then H is equals to image section of AD1. Then we have the function in pixel region of H. Now we can easily notice the which type of coefficients, whether it is a horizontal coefficients or vertical coefficients, we are going to see now. Can anybody give me the answer? Which type of coefficients we are going to fetch now? Vertical or horizontal?
Vertical.
Vertical. So let us find out now. See here, if you go towards the extreme left, and at the top, you can easily notice the coefficients. See here. So these are the vertical coefficients. And if you compress, if you just compress this starting column, the rest of the frequencies are not that much repeated. So this is the only which contains highest value: 489, 617, 25671, 3477. That is why these are the components which contains a maximum value. So if you compress this single column, it is more than efficient for us. Okay. So similarly, we have a sidebars also. So another image, that is what we can say C image, which is equals to IM read of sidebar. SP, okay, fine, SP.jpg, I think. So I'm going to convert this into intensity image. Now I'm going to display this image. So this is how it looks because it is a sidebar. It contains diagonal coefficients. Let us find out the DCT components of the sidebar image. Okay. So once again, I'm going to same thing. AB3 is equals to DCT2 of C. That is sidebar image, and H is equals to image section of AD2, AD3, I think, because I have used the function AD3 as a variable. Then image IM pixel region, of H. Now we can notice the diagonal coefficients here. Just roll over this to the extreme left and to the extreme up. See here, you can notice the diagonal coefficients here. Okay, so if you compress the diagonal layer, or we can say the diagonal values of a given matrix in a given frequency domain concept, you can easily compress the given image with respect to the sidebars. So this is all some of the brief information I want to highlight all of you about the application of discrete cosine transformation in case of image compression. Okay, dear students, I hope the session is informative for all of you. So with all this, I want to give a statement for all of you now. So this is just beginning of image processing. This is not the end of the image processing. It's the first step for all of you to just explore the different various concepts present in image processing. The next higher version of image processing is a computer vision. Of course, pattern recognition is there. Machine learning is also there. Classifiers, pattern classifiers are there. These are the different mechanisms we can use in order to recognize, like supervised learning, we have unsupervised learning, in order to find out a given object recognition. Okay, maybe the application is very huge. CCTV surveillance lines. We have a different type of image recognition, like face recognition. I think your mobile also supports all those features. So wherever you go, this application of image processing definitely will play a huge role. Okay. So with all this, I am going to stop my session here. Not only my session, this is the end of the image processing syllabus, not concept syllabus. Okay, because concept is a huge. You can explore more and more. I have just made a fundamental layer for all of you, and you can build more and more on these concepts. Okay, so if you have any queries, any ambiguities, any questions, clarifications, I will conduct another class if you need. Okay, so with all this, shall I conclude? Yes, dear students.
Yes, sir.
So how was the session? How was the syllabus? How was the concepts? Everything? Yes.
Interesting, sir.
Okay, fine. Very good. So keep on learning these new concepts. Okay. So whenever you have any doubts or clarification, you can approach me in the department also. You can visit. I'm going to share all the materials related to the fifth module. After the session is over, today only I'm going to upload them in the WhatsApp through the Google Classroom also. I request some of the students to upload your assignment, only few, 2 or 3 members remaining. I request all of you to please kindly upload your assignments. So thank you so much for your patient listening in the entire journey of image processing, and we have reached the end now. We have reached the shore. Definitely there are still more things to learn. Exam perspective only, syllabus perspective only. I'm stopping here. So I wish all of you wholeheartedly all the best for your examinations, because in present situation the university is planning to conduct offline examinations. So please be serious. So consider the studies very serious. Please thoroughly study all the materials, whatever I have given for all of you. So thank you so much, dear students, for your presence and for everything. Thank you so much. So wish you all the best for your examinations. Thank you.
Thank you, sir.